This is 3.7 day 2 homework. Explain why a function defined by a element of degree 4, that means it's an x to the 4th equation, with real coefficients has either 0, 2, or 4 real answers. Okay, so there has to be 4 solutions. Okay, and we also know that the non-real come in pairs. Okay, so if it's I, negative I is an answer. 2 plus I is an answer, 2 minus I is an answer. They have to come in pairs. So therefore, if there has to be 4 answers, it has to either be 4, 2, or 0 real solutions. Okay, because the other two or 4 have to be imaginary then, or 0. Okay, 45. Okay, whether it's possible. Okay, so for part A, if I have degree 3 with these zeros, that would be impossible, because if this is a solution, I know that 2 minus I has to be a solution, which would give 4 of them. So not possible. 45B, if it's a degree 4, so that means there has to be 4 total answers, has 4 non-real zeros. Yep, that's possible as long as it adds up to be 4. C, if it's a degree 5, it has to be 5 solutions. Negative 6 is a 0 multiplicity of 6. Okay, if it's a multiplicity of 6, that means that it happens 6 times. If it's degree 5, we can only have 5 answers, so we can't have 6 answers. Six zeros is not possible. I'll say 1 minus I also has to be. Okay, D, if 1 plus 2I as a 0 of P of X has 1 plus 2I as a 0 of multiplicity 2. That could happen. It just means that 1 minus 2I would also have to have a multiplicity of 2. So that's possible as well. Okay, 46. Suppose that A, K, A, B, and C are real numbers, not equal to 0, and the polynomial. Okay, so we have this polynomial here. Okay, so what degree will it be? Okay, so if I multiply this, x times x, ax squared would be ax to the third, right? So it would be x to the third, degree 3, would be our highest exponent. How many distinct real zeros would there be? We could have 1 0, 2 zeros, or 3 zeros, right? We need 3 solutions. Some of them could be doubles or triples, okay? So there could be multiplicities of them, but at most 3. Possible non-real. Remember, they always come in pairs, so I could have 0 non-real, so imaginary, or I could have 2 imaginary. I can't have 4 though, because it's only x to the third. And use the discriminant. So the discriminant is that is this part here, right? Okay. To determine the number and type of zeros. This will tell us if it's negative, it yields non-real solutions, or zeros. Okay, next one's 48. Okay, we have x to the third plus 5x squared plus 2x minus 8. Okay, so given list all possible rational zeros, use a graph to eliminate some of the possible zeros listed in A, and then find all rational zeros, and then you turn them into factors. Okay, so if you remember, our P was negative 8, our Q is 1. Just notice you can't see that. Let me move this over for you. Okay, our P is the 8, negative 8, and our Q is the negative 1. So our factors of negative 8 would be plus or minus 8 and plus or minus 1, or plus or minus 2 and plus or minus 4. Of 1 is just plus or minus 1. So the possible answers could be 8 over 1, or 8 over negative 1, 1 over 1, or 1 over negative 1, 2 over 1, or 2 over negative 1, 4 over 1, or 4 over negative 1. Okay, so those are our possible answers. Okay, you can use a graph to eliminate some of the possible zeros. Yeah, so if you look at a graph, it would actually give it to us very easily what our zeros are, right? It would intercept at, if you look at a graph, at negative 4, at negative 2, and at 1. Okay. So if you go to Desmos and graph this whole thing, it tells you what exactly the zeros are. So it says you use the graph, find the rational zeros. So our rational zeros were negative 4 works, and negative 2 works, and positive 1 works. Okay, so those are my rational zeros. Also, just take them and plug them in, right? 1 to the third is 1, 1 times 5 is 5, 1 would be 6, and 1 times 2 is 2, 6, 7, 8, 8 minus 8 yields 0, okay? If I plug negative 2 in here, it also gives me 0. Plug negative 4 in there, it also equals 0. Okay, so those are all my, so I know that my zeros are x equals 1, x equals negative 2, and x equals negative 4. So then part D, it says the factors would be x minus 1 times x plus 2 times x plus 4. So those would be my factors. Okay, number 51. I have the equation 6x to the third plus 17x squared minus 31x minus 12. Okay, now this one's going to be a little bit longer, because my p is a negative 12 and my q is a 6. So there's more factors here. So we have 1 and 12. We have 2 and 6. We have 3 and 4. And on the bottom here I have 1 and 6, and 2 and 3. So if I list all those factors out, all the possible factors, okay, 1 over 1 would be 1 and negative 1. 1 over 6 would be 1/6 and negative 1/6. 1 over 2 would be 1/2 and negative 1/2. 1 over 3 would be 1/3 and negative 1/3. Okay, let's go to the 12 now. 12 over 1 would be 12 and negative 12. 12 divided by 6 is 2. 2 and negative 2. 12 divided by 2 is 6. 6 and negative 6. 12 divided by 3 is 4. 4 and negative 4. I'm going to have to make another line here, I think. Okay, so I took the 12 through, let's take the 2 through. So 2 over 1 is 2, which we already have. 2 divided by 6 is 1/3, we already have. 2 divided by 2 is 1, we already have. 2 divided by 3 is 2/3, we don't have. Okay, now we'll go to the 6. 6 divided by 1 is 6, we have. 6 divided by 6 is 1, we have. 6 divided by 2 is 3, we don't have the 3 up there yet. 6 divided by 3 is 2, we have the 2's there. 3 divided by 1 is 3, that we have. 3 divided by 6 is 1/2. 3 divided by 2 3 divided by 3 is 1, we have. 4 divided by that, we got 4. 4 divided by 6 is 2/3, we have. 4 divided by 2 is 2, we have. 4 divided by 3 is not there yet. Alright, so now to decide which one of those are actually factors, you can use Desmos, or you could take the answers, all these choices, and plug them in there, Or you could use Descartes' law of sign changes and the boundedness theorem to figure some of that out and eliminate some of them as well. But just using Desmos, we find the answers there. Okay, so we know that x is equal to -1/3, x is equal to -4, and x is equal to 3/2. Okay, now this one's very simple. You could put into a factor is just x plus 4. Okay, these are a little bit tougher. Let's think about this. It'd be x plus 1/3 and x minus 3/2. Okay, but generally we don't want to leave them as fractions like this. We're gonna say we just multiply it by both by 3. It'd be 3x plus 1. Now, if I would set this equal to 0 or that equal to 0, both of them give me -1/3, right? And here I'd multiply it by 2, so this would be 2x minus 3. If I set that equal to 0, I still get the 3/2. Okay, number 54. Okay, number 54 says to use irrational zeros, so thinking about all the rational zeros that are possible to create factors. Okay, so these are 12 over 12 is 1, 12 over 1 is 12, 12 over 2 is 6, 12 over 6 is 2, 12 over 3 is 4, 12 over 4 is 3. Okay, then we're going to use the 1, so we have, there's a lot of these here. 1/12, -1/12. 1 over 1 is 1, got that. 1 over 2 is 1/2. 1 over 6. 1 over 3. 1 over 4. Okay, go to the 2 over 12 is 1/6, 2 over 1 is 2, 2 over 2 is 1, 2 over 6 is 1/3, 2 over 3, don't have that one yet. 2 over 4 is 1/2, have that. Okay, go to 6 over, be 1/2, 6 over 1 is 6, 6 over 2 is 3, 6 over 6 is 1, 6 over 3 is 2, 6 over 4 is 3/2. Okay, 1/4. Is 1/4 there yet? Yep. So that's the 3 over 12 is 1/4. 3 over would be 3. 3 over 2 is 3/2 is there. 3 over 6 is 1/2 is there. 3 over 3 is 1. 3 over 4 is 3/4 is not here. Okay, 4 over 12 is 1/3. 4 is there. 4 over 2 is 2 is there. 4 over 6 is 2/3 is there. 4/3 is there now, and 4 over 4 is 1. Okay, so there are a lot of them here. Okay, and number 54, I'll just tell you it comes up to be the ones that work will be -3 over 2 works. -4 over 3 works. And -1/2 works. Okay, so those are the three that if you plug them back in here, they will equal a 0. So our factors, if x equals -1/2, and x equals -3 over 2, and x equals -4 over 3, our factors would be x plus this 1/2, x plus the 3 over 2, and x plus the 4/3. Okay, now if I get rid of the fraction with them, multiply this one by 2, it would be 2x plus 1. Multiply this by 2, it would be 2x plus 3. Multiply this by 3, it would be 3x plus 4. Okay. 57. Find all rational zeros of each polynomial function. Okay, so we have x to the third plus 1/2 x squared minus 11/2 x minus 5. Find all rational zeros here. Okay, so let's do the p and q again. P is -5, q is 1. So this one's a lot easier. So it's just plus or minus 5, plus or minus 1, and plus or minus 1. So we have either 5 over 1, or 5 over -1, or 1 over 1, or -1 over 1. Okay, so those are the only possibilities there. Oh, actually, that's not right, because we have to first multiply it. We can't have fractions here, so we got to multiply it all by 2. So it'd be 2x to the third plus 1x squared minus 11x minus 10. So that's what we have to use. So the p we're going to use is 10, and the q we're going to use is 2. Okay, so it'd be 10 and 1, or 5 and 2, and this is only 2 and 1. Okay, so we have 10 over 2, which is 5, 10 over 1, 1/2, 1 over 1 is 1, 5 over 2, -5 over 2, 5 over 1, which we already have, and 2 over 1 is 2. Okay. So those are our possible choices here, and they come up to be the ones that work. Is 5 over 2, and -1, and -2. So our zeros are -1, 5/2, and -2. Okay, number 60. Okay, so we want to get rid of the fractions. Let's multiply it all by 6. So we get 6x to the fourth minus x to the third plus 4x squared minus 1x minus 2. So our p is -2, and our q is the 6. So this is just 2 times 1, and then 6 times 1, or 2 times 3. Okay, so 2 over 6 is 1/3. 2 over 1 is 2. 2 over 2 is 1. 2/3. Okay, take the 1 through, so it'll be 1/6. 1 over 1 is 1, we already have. 1 over 2 is 1/2. And then 1/3. Okay, and the ones that work, if you plug these numbers back in here, which ones equals 0? For the 0, the function is -1/2 works, and 2/3 works. So there'd be 2 others that are imaginary answers, but we have x is equal to 2/3, x is equal to -1/2. Okay, 63. We have p of x is equal to 21x to the fourth, 13x to the third, minus 103x squared, minus 65x minus 10. We want the factors. Okay, so we're putting it all together here. It says to use rational zeros theorem. So it'd be 10 and 1 and 2 and 5 for the 10, and the 21 is 1 and 21 and 3 and 7. So 10 and -10. I'm gonna edit this. It's only going to be through 60, not 63. Okay, number 72. Use a sign change. Okay, so the sign change for our p of x, okay, is one sign change. Okay. Therefore, our one positive. Okay. Or, okay, if I find p of negative x here, so negative x to the, I'll write it out, negative x to the third plus 2 times negative x squared plus negative x minus 10. Okay, so this would be negative x to the third. That'd be a positive 2x squared. Be negative x minus 10. So there are 1, 2 sign changes. Okay, so there's either 2 or 0 negative. Okay. Okay, and the actual, then use a graph. Okay, so if you look at the graph of this, go graph this on Desmos. Okay, if you look at the graph on Desmos, it has 1 positive number and 0 negatives. So that means there's 2 imaginaries there. Okay, 75. Okay. Whoops, sorry, you couldn't see that. Hopefully you can see that. Okay, so sign changes here. There's positive to positive to negative and negative to positive, so 2 sign changes. Therefore, there is either 2 or 0. 2 or 0 positive. Okay, and then if I find p of negative x, that makes that negative x to the 5th. That stays positive there. That changes to be positive. This would be negative 2x. Okay, so there'd be 1 sign change, 2 sign changes, 3 sign changes. So 3 sign changes. We're either 3 or 1 negative. Okay, and actual from the graph. Actual from the graph, you get 0 positive and 1 negative. So that means there would be 4, since it's x to the 5th, means that there would be 4 that would be non-real. Okay, 78. Use the boundedness theorem to show that the real zeros of p of x satisfy the condition. Okay, so let me write this function down first. Okay, so we want to prove that there's no real greater than 1. Okay, so let's take 1 and divide it out. Okay, that'd be 1x to the 5th, 0x to the 4th, 2x to the 3rd, negative 2x squared, 5x, and 5. I'm using synthetic, just a little easier. That'd be 1 times 1 is 1, add together, 1 times 1 is 1, add together, 3, add together, 1 would be 6, 1 times 6 is 6, add together is 11, okay? And then our theorem, boundedness theorem, said since all non-negative, okay, they're all none of these answers are negative here. Since those are all, that proves that there's no real 0 greater than the 1. Okay, 81. Our p of x is equal to 3x to the fourth, 2x to the third, minus 4x squared plus x minus 1. Once again, no greater than 1, so we're going to divide that 1 out of here. 3x to the fourth, 2x squared minus 4x plus 1 minus 1. Okay. 1 times 3 is 3, 5, 1, and 1. Okay. Once again, all non-negative. So therefore, no real 0 greater than 1. Okay, 83. We have x to the fifth minus 3x. Whoops, you can't see that. Minus 3x to the third plus x plus 2. We want to prove that there's no greater than 2. So we're going to divide out the 2. 1x to the fifth, 0x to the fourth, negative 3 third, 0 squared, 1 and 2. 2, 4, 2, 5. Okay, once again, all non-negative, therefore no real 0 greater than 1. Okay, I should have given you another one, like 80. I should have given you 84 instead of 83. Actually, I didn't even give you that. I only gave you 81. But also the other theorem said that if these are all opposite signs, then there's none that's going to be less than this number. Okay, so they also had that theorem too. So you didn't actually have to do that one. All right.